G'day YouTube and welcome back to the ASX Portfolio channel. My name's Jonathan speaking. So today we're going to be talking about American put options. Now we're going to be talking about American options in general. We're going to explain why it's never optimal to exercise an American call option on an underlying that doesn't have a dividend and there's no negative interest rates in the market. We're also going to be implementing American put option pricing in Python with a slow function, and then we're going to use numpy arrays to speed that up, and we're going to create a fast function. So stay around for that. If you're more interested in the programming, please skip ahead to the end. So here we're going to go through the theory. So an American put option differs from a European option in that it has a different payoff function. So how is the payoff function different? Well, we still have these terms here. We still got K strike, we still have got an underlying S, and we still got a expiry time. The payoff function looks similar for a put. So we've got K minus S, but you'll notice here we have tau. Now this is because you, the holder, can have an exercise time of your choosing. So we're denoting this using tau, and this is less than or equal to T. So now we're going to tackle why it's never optimal to exercise a American call option with an underlying that doesn't have a dividend and interest rates are positive. So let's jump into the math. So for this example, we're going to be taking a exercise out of the John C. Hull Options, Futures and Other Derivatives book. So to understand this, we're going to consider two different portfolios. Now first, a call option, remember, is the right to buy a share at a certain price level. And now we're calling this strike K at a certain time in the future. Now with the American option, you can choose when this is going to occur. Now really the reason why it's never optimal is because if you were to exercise, you would have to pay that K strike today, and you would lose out on the interest that would be saved during that period of time that you could keep that K dollar value in your bank account. So let's see that on the board. So let's picture a portfolio today where you have an American call option, and remember you're going to have to pay the K strike at expiry. So K, and we're going to discount that back to today. So we're going to use the risk-free rate from expiry to today. So this is the value that we will eventually have to pay at expiry. So we have to have this amount of cash on hand. So the second portfolio is simply going to have the underlying, which is S. Now remember, see here, that has a payoff of S minus K, where S tau can be exercised at any time. So now we're going to consider the conditions where V1 and if it's ever greater than V2. So let's consider two different scenarios. One where we actually exercise this option before the final time, and then one where we exercise it at time T. So let's consider what our portfolio one holds at this time. So here we'll have the call price. So we'll have S tau minus K, so the max of 0 or this value, and we'll also have the money invested in the bank account, which will be the discounted price of that strike K, so T minus tau. Now, as you can probably already see, this is always going to be less than V2, which is equal to S. So this value on the left-hand side, the value of this, no matter the circumstance, is always going to be less than portfolio 2, where we just have the share price. Now, in contrast, if you look at tau, where it's equal to T, then you can see that the portfolio value at the end of portfolio 1 is always going to be ST minus K and the max of 0 or that value. Now this plus K, because now you no longer need to discount the strike price, you'll have to pay K. So what does this mean? Well, this means that this value, no matter what ST ends up being, is always going to be greater or equal to our V2, which is the price of the share. For all times, you should not exercise an American call option early because of the continuation value that you get is larger than the amount that you would be exercising for today. Now, in comparison, an American put option is the right to sell that price at price K. Now, if you were to exercise early, then you would receive K and you would be able to invest that in a bank account and receive the risk-free rate interest rate. Now, this has the potential to be, this exercise value, has the potential to be greater than the continuation value depending on which circumstance you are in your tree. So if you can picture that we have this probability in our tree starting from the price today, let's say for example that you get down to here in the tree. Well, potentially there's not much further that you can go at this time period in the tree where the continuation value is going to be worth much to you. So therefore, it's better to exercise that put option at this point in time and then put that money in a bank account, earn the interest-free rate, and you'll end up with a much larger payoff, well, a larger payoff. So intuitively, hopefully it makes sense. You wouldn't exercise an American call option because you'd have to pay K today and then not get the interest to the future. Whereas for an American put option, when you exercise early, you will receive K value and you will be able to invest that in the risk-free rate and actually get some value out of that. Now, that will only be worthwhile exercising early if the continuation value, so the expected discounted value of the payoffs on that trajectory, is less than that exercise value today. So it's very dependent on what the interest rate is of that risk-free asset and the bank account. Now, an interesting concept to this is if that is a negative interest rate, well then there's going to be cases for the call option where that is of a benefit to you to exercise early. So two conditions which I think it's quite funny to talk about is that one, what happens if we have negative interest rates in our risk-free bank account, and two, what happens if we have dividends? Well, obviously if you have a dividend and the continuation value is less than the amount if you exercise today and then receive that dividend with the American call option, well then of course you should exercise. And again, thinking about the negative interest rates, if you're getting paid to take money out of your bank, then you're able to actually exercise today, take that money from the bank account, K, to pay that strike, and then you're holding the share, and then you've getting an interest from the bank account by borrowing that money. So there are cases under these conditions where it may be optimal. So those are just some things to keep in mind. Now, there are probably another couple of conditions that you could put on here, like what happens if your American call option wasn't going to be traded in the future, things like this, or it wasn't going to be worth anything because of one reason or another. Then there's probably many cases where you would want to exercise your American call option at the start. But traditional finance knowledge should be that it's never optimal to exercise with a non-dividend paying underlying, because the continuation value is always worth more. Okay, so now on to the American put pricing in Python. So we're going to do a American tree slow and an American tree fast using the American option theory. So we're going to import numpy. That's probably the only dependency you need to import. We're going to be using a generic timing wrapper. You don't need to import this to actually benchmark our slow and fast option pricing models. So how are we going to represent this tree? Well, we're going to use the binomial tree representation. So this is just a bunch of nodes I and j with initial stock price SO. You can calculate the price of SI, the stock at each of these ij nodes using this formula, the up and down factors here. And we haven't talked about how to actually calculate those up and down factors yet to get a realistic distribution in terms of the volatility of the asset. We're going to be doing that in the next video, so bear with us. Here we've got C, which is the contract price at each node. Now this is going to be represented from our payoff function, and it's going to be discounted back to the time today. So for the American option, we've got some characteristics here. We have For a put option, we're going to be specifically talking about here, because for a underlying that does not pay a dividend and there's no negative interest rates, the call option, American call option, can be valued using the Black-Scholes formula. So here we're going to be pricing an American put option. So the terminal values we're going to set at the end of the tree is K minus SJN plus. So we're going to create this tree as if we're not going to exercise early. So the unexercised value of this tree. So for all other parts of this tree, we need to take the max of the exercise value. So what is the exercise value worth to us today? And that is K minus S. Now, thinking about that, we can take that money, put it in a bank account, and that value could be greater than the continuation value. What is the continuation value? Well, here we're discounting back today for that point in time at that node, the risk neutral pricing of the two possible outcomes. So our up outcome and our down outcome. So the risk neutral pricing, our continuation value, our discounted expectation of the payoffs compared to what our actual value for exercising this put option is today. So whichever one is greater, that's the value we're going to take for that particular node. So excellent, let's jump into it. So we've got our initial parameters here, just copy them from my website. Initial stock price, strike price, time, annual risk-free rate, the number of steps, up factor, down factor, and we're taking the option price to be put. Now we're actually going to implement the call option as well in here, because we will be using these functions later on in our series. So let's get into it. Let's create a American slow tree function. And here we're going to be taking in all those values, K, T, SO, the other factors are N, the number of steps, the up factor, the down factor, and the opt type, which we're automatically assigning P. Cool, so here we're going to pre-compute our values as we have been doing in the last couple of tutorials. So here our time step is just going to be that total time divided by the number of steps, N. We're going to take Q, which is going to be equal to that numpy exponential R times dt, and that's going to be minus by the D factor divided by U minus D. So now we've got the discounted value for each time step, and that's just going to be equal to mp.exp minus R times dt. Great, so now that we've got our pre-computed values, let's actually use them. So let's initialize, as always, our stock prices at maturity. So we're just bringing these prices forward, SO today. Let's initialize a numpy array of zeros, and we'll take that to n plus 1, because remember, if we're going out n time steps, then our actual number of nodes is going to be n plus 1. So here we've got for j, so for the node in range 0 through to n plus 1, then we're going to add sj is equal to that price times by u to the power of j times by d to the power of n minus j. Excellent, so that's our formula for the underlying. Make sure that that's a capital S, so we're actually indexing correctly. Great, so now we have to check the option payoff. So remember, we're considering the tree for the American pricing of a unexercised option, so let's take those payoffs. So again, we'll just initialize this C call option price with zeros for n plus 1, and we'll do the same thing. We'll go for j in range 0 to n plus 1. Then if opt type is equivalent to P, then what we're going to do is call Cj equal to the max of 0 or k minus sj. Now, if it's the call option, which will be else, we'll do the opposite. So we'll go max of 0, s minus k. But again, here we're only focusing on the put option in our example. Now, cool, we need to do the backward recursion through the tree. And applying this formula, the max of the value, exercise value, or the continuation or hold value. So backwards through the tree, how are we going to do that? For I, so the time step in the numpy arrange n minus 1 down to 0, but we have to go to minus 1, taking minus 1 time steps through this tree. So from n minus 1, the second last column in our tree, all the way back to time 0. So for each of those time periods, each of those columns, we're going to iterate through the rows, through the nodes. So in range 0 through to I plus 1. Now that's I plus 1 because we want to get to I. So S is we're going to have to compute S each time now, because this is going to be dependent on our continuation, our exercise value. So we're going to take that as being J times by D to the power of I minus J. So instead of N minus J, it's I minus J, because we're changing the length of that column each time we're stepping back in time. And that is going to be Cj is equal to, now it's going to be the discounted payoff, risk neutral payoff of the prices before. So J plus 1 plus 1 minus Q times Cj. So again, this is just the risk neutral pricing approach that we've gone through before. Now, we've got this value. Now we need to consider what the exercise value would be. So if opt type equals put, we can probably just copy this from here. If opt type is a put, then we're going to have the continuation value being equal to this. Now, instead of the max of 0, it's going to be the max of Cj, which is that continuation value we've just calculated, or the actual exercise value. And it's going to be the same thing for the call here. Cool, so now that you've got that, all we need to do is return that value of the option. So it'll just be C0. So let's calculate that value with all those predetermined constants, and we get our value for the American tree slope. Now let's do the same function, but make it faster using numpy arrays. Why is it going to be faster? Because we're going to vectorize these calculations using numpy arrays without iterating through those nodes J. So how can we do the initialize of stock prices more efficiently? Well, we can do this all in one step. So we can calculate SO, we can multiply it by D to the power of, and we can take an NP arrange, so an array of values, and we're going to take n to minus 1, taking -1 steps. Now that'll be the D factor, and now we need to multiply by the U factor to the power of NP arrange, and that'll be from 0 to n plus 1 with 1 time steps. So now we just need to do the option payoff. How could we do the option payoff all in a couple of steps? Well, instead of making that zeros, instead of iterating through the nodes, we can just say if the option price is P, what are we going to do? Else, if it's a call, what are we going to do? So let's go C, we're going to take np.maximum, and we're going to take the maximum of 0 and k minus s. And we're just going to do the same thing for the call, except that'll be s minus k. Great, and that should give us our payoffs vector. Now we've got backward recursion through the tree. We're no longer going to be doing this j step. So each time we step through a time of the tree, we need to be calculating the full array again. So we can just copy this function here, but instead of using n, we're going to use I for the time step, I. And here for C, we're going to be calculating the risk-neutral pricing at each time step. So discounted value is correct, but we need to do some sneaky maths here. So we're going to use slicing, and this is going to be I plus 1. Here we're going to be taking 1 to I plus 2. And then here we're going to be, it's default, but we'll do it anyway, 0 to I plus 1. Excellent. So that's looking good. Now here we just need to do the same thing as above, so I can just copy and paste that. One thing this function is going to require though is for S and C to be the same length. So what we're going to need to do for that is actually slice this C by -1. So not take the last value that we're knocking off every time that we step back through the tree. So now that we've got this, we should be able to run it. Let's call it something different. So I've called it slow. Let's call this fast. Great, and run that. So let's find out the difference between these two different methods of calculating the trees. So you can see that the first couple are quite quick because they've just got a few nodes. The fast one with 5,000 nodes has taken 1.3 seconds here. And you'll notice that this takes a lot longer, the slow function, now compared to when we were valuing the European option and the barrier option, because really we're iterating through quite a few steps here. Having to go through and compare the max of each price at each node of the exercise versus the continuation value. Now you can see that the slow tree still hasn't even finished there, and it's going to take a lot longer. So hopefully you can see the value of actually using numpy arrays to speed up these calculations. I just want to say thank you very much for listening and getting to this point. Binomial pricing models were really created for pricing American options, and I think that it's a great way to do this. So stay tuned for how you can actually parameterize those U and D factors and get a gauge of your volatility in the market to your underlying. So stay tuned for that, and until next time, YouTube, catch you later.